So the next speaker is Eric Swains, talking in modular stabilization of heterotic string theory with Flux.
Okay, I would first of all like to thank the organizers for letting me talk here today. This is a continuation of the talk that Michael gave earlier on where we consider the E8 E8 times E8 heterotic string on these domain wall solutions, where due to the fact that the setup is such that this compact part of your geometry will then be maybe given a torsion, which means that might help to stabilize moduli, we'll come to that later. There's a drawback though that a preferred direction is singled out, which is away from the domain wall, and you have to work to get rid of the y dependence of the fields. So supersymmetry will imply that this semi-direct product Ry times the internal space, it's basically a G2 cone, so it has a G2 structure, and this in turn gives X the structure of a half-flat SU3 structure basically, and we'll take X to be as Michael said, we're taking X to be a homogeneous space, that is a Lie group modded out by a sub-Lie group. So why homogeneous spaces? Well, first there's a few known examples of half-flat compact spaces, and secondly one can write down these the various quantities explicitly, which is a nice feature, and also H3 of all these spaces, all the 4 different spaces that occur is in fact 0, so there are no complex structure moduli to worry about. And so, as Michael said, we are requiring the elements of our theory to be G invariant under the action of this parent group G, which makes things simpler, and the quantities are easier to handle. And focusing on the example SU3 over U1 squared, which is the most terminologically interesting one, where bundles constructions are ambient, this space has 3 G invariant 2 forms and dual 4 forms, and 2 symplectic G invariant 3 forms, alpha 0 and beta 0. And as for Calabi-Yau, one can expand the Kähler form and the complex 3 form in the internal geometry. And again, G is then a second order homogeneous polynomial in this Z parameter, and which we call the pre-potential in relation to the Calabi-Yau setting. So we heard from in Michael's talk that this domain wall solution will these solutions can solve the supersymmetry equations and the Bianchi identity exactly, and the equations of motions are solved up to order alpha prime squared over r to the 4th, and we'll want to turn to see if we can match this 10D solution to a 4D supergravity basically. And in order to
So what's your ultimate goal? Do you want to get rid of the domain wall, and you want to find
exactly,
Minkowski?
You want to be in a what?
I mean, do you want to find a Minkowski vacuum? Or
well, it turns out it's going to be an ADS vacuum, but yes. Or you want to be.
So that's a goal.
Yes.
Okay.
Precisely. So the NS2 form, 2s and 3 forms are expanded in terms of the internal geometry, and this parameter mu here now is a constant up to order alpha prime squared. That's a technicality, but that's determined by calculating the Chern-Simons 3 form of the various bundles that you use, and the parameter mu is then going to be dependent on the internal geometry. No, wait, it's going to be dependent on the bundle that you use basically, and the bundle parameters can be positive and negative, and that will have consequences for which moduli you're able to stabilize basically. And so again, as in supergravity, one defines the complexified Kähler moduli and an axiodilaton and their corresponding superfields, and we calculate a Kähler potential and a superpotential, where we have a constant piece here, since G is homogeneous of degree 2, and this piece here is then a constant term added to the superpotential, which help us to stabilize things. Well, we will see how, exactly. So in order to look for supersymmetric solutions for the theory, so supersymmetric vacuum where the fields are constant, it's with respect to these domain wall directions, you find from the 4D killing spinor equations that that's equivalent, in fact, as to having the n equal 1 if you want n equal 1 supersymmetry, it's equivalent to setting the f terms to 0, which is exactly what you have in the in the usual case. Okay, so that can easily be done for the first two covariant derivatives corresponding to the first two Kähler moduli, which these two equations imply that v1 and v2 are equal 0, and this is the nearly Kähler locus that basically we really heard about in the previous talk. And also it should be mentioned that this is the same locus that you end up with if you set the d terms arising from these line bundles to 0. So yeah, and it's equivalent. In fact, you get the exact same equation, and you can show that it's equivalent to the 10D Young-Mills equations. Okay, so moving on, we tried again to set the covariant derivative with respect to the third Kähler modulus and the dilaton to 0. We find that this is in fact not possible. We get either a constant v3 and a dilaton blowing up as y goes to infinity away from the domain wall. And that's for the case mu less than 0, or alternatively you get a v3 modulus blowing up and a constant dilaton. And that, yeah, and that's, I mean, you can compare and see that this is the same that happens in the 10D case. And well, we conclude that although you can't stabilize all the fields, you can at least stabilize all the internal fields with a runaway dilaton direction when mu is less than 0. So what we try to stabilize the dilaton again, well, if you want to stabilize the dilaton, you need to make W dependent on the dilaton basically. And that could be solved by adding non-perturbative effects such as a Gaugino condensate. Yeah, that's a typo, unfortunately. Now here K is a constant of order 1 in units of alpha prime, and this C here is a number depending on the condensing gauge group, and you have a so the condensation happens in the hidden E8 of the E8 times E8 theory. So yeah, so there's a problem that arises that we find a tension between having these all requirements that we want consistent. So for instance, we want K of order 1, and we want the non-perturbative effects to be small. And we want a weak coupling at the gut theory should be at weak coupling and a large volume. And yeah, for mu less than 0, however, we see that if K is chosen to be large enough, that is for this, I mean, K is at K min, you see that you get okay. So first, this plot is for K less than K min. This is for K at K min, and that the dotted one is for K more than K min. And you see that above this value K equals K min, you can in fact stabilize all moduli. The price you pay is that yeah, this, I mean, depending on the value of this parameter mu, so K will actually increase with the increased mu value, which is basically, so the value mu depends on the bundle parameters, as I said earlier. And if mu is large, this implies that K is large, and this, as K is generically of order 1, this implies fine-tuning basically. So also, as in the Calabi-Yau case, to first order you identify the axial dilaton with the gauge kinetic function, and so weak coupling then corresponds to a large value of this x. Yeah, this x here is the basically c times the axial dilaton. So yeah. And the supersymmetry equations, I mean, these two extrema here are supersymmetric, so the d terms vanish. Now the f terms vanish at these points. From the supersymmetry equations, you see that this implies that if you want x large, you have a small v or the small v3, and vice versa. However, it can be solved. As I said, you find this competition, but it I mean, the larger the value of K, or the larger the value of mu, equivalently, the better the I mean, solutions. Basically, so I should draw something. So okay, so for instance, basically increasing the value of k, means that you can, the better, the larger values you choose for k are equivalently, you can choose bundles for which, you can set this as large as you want with just choosing the bundle appropriately. However, this implies that in order to get extreme of the potential, you need to set this k large, and that's requires a lot of fine tuning. But if you don't care about that, then nice values for x and v are possible. So concluding, so we see that to first order alpha prime, the internal moduli can be stabilized, all of them. And if you add non-perturbative effects, you can also, to a certain degree, stabilize the remaining dilaton, although this is going to be at an ADS vacuum. And so this might give you motivation to explore the physics beyond, take these models further and see what actual phenomenology you can do for these. We've just required that you have you have the first Chern class vanishing so that you get correct the gut groups, and you also have demanding 3 generations, for example. Yeah. Well, but so one reason one might want to try and do phenomenology in this case is that calculations are easier in the sense that they become group theory calculations rather than algebraic geometry or stuff like that. So, in worst case, one can still learn something about the physics of non-Kähler complex factorifications if it turns out that they don't produce any viable physics. So, yeah.
Questions? Yes.
So what did you have before the non-perturbative effects? Was it kind of a supersymmetric no-scale Minkowski solution?
No, it was. Yeah, no, it was. Well, it wasn't a. So basically, you had it's not night. So basically, it's a runaway direction for one of the. This y direction is yeah. So you have an.
So it's still a domain wall then.
Yeah, exactly. Yeah. Mm. Yeah.
More questions? Okay, let's thank the speaker.